Now, for those of you who like formulas, we can think about this PQ. Remember that PQ is simply a point we are looking for. Let's call it x, y, z, and a point on the plane. Let's call that x1, y1, z1. Given that, you can actually create a pretty good formula here in terms of just breaking this down. So vector PQ, remember, would be composed of three things: x minus x1, y minus y1, z minus z1, right? That would take you, just do your destination minus origin. And then we're doing a dot product with the normal. Now, the normal of the plane we know is simply a, b, c. And the magnitude of the normal would be the square root of a squared plus b squared plus c squared, right? That would be the magnitude of the normal on the bottom. Now, you take this same equation and you go down to the next line, and the dot product we know is the x coordinates multiplied by each other. So we'll do an a times this x1, y1. Okay, we'll do, and then the dot product adds the two y's multiplied by each other, and then adds the z's multiplied by each other, right? So we're not dotting with ABC. We did the dot of ABC, and we did a times the x, b times the y, c times the z. Now, what happens here, if we expand that top part, you get ax minus ax1, right? by minus by1, cz minus cz1, right? All I'm doing there is just expanding, distributing the variables throughout the brackets. Now, the reason that this obviously it doesn't look like a nice formula, but what we need to do here is just do a quick separation of the parts, and you'll see how this could be useful. If I do ax plus by plus cz, and then I do minus ax1 minus by1 minus cz1, I remember from earlier, right, that expression a, b, c times a point on the plane was another way of expressing the d value from the equation, right? So I can go down here and I can go, okay, that means the distance from a point to the plane is equal to this plus d over root ABC. So again, if you like formulas and the projection thing is giving you a lot of trouble and you want to memorize the formulas instead, this would be an option. Just keep in mind here that x, y, where x, y, z, are the coordinates of the point you're interested in, and ax, by, cz plus d equals 0 is your plane that you're measuring to. Okay, and that's that section. So we have a good formula in terms of to get the distance from a point to a plane, and I think at this point we are ready to start whatever work it was they were asking us to do. So find the scalar equation of the plane that passes through 2, 1, 1 with the following normal. Okay, again, a very, very straightforward place to start. And you can imagine how we're going to do this. We know what the answer has to look like. We're just going to fill in everything we know and make it work. So let's see. So we know the answer is ax plus by plus cz plus d equals 0. That's the equation of the plane. We know that a, b, c has to be equal to 3, 4, 5. Okay, which tells us that we have 3x plus 4y plus 5z plus d equals 0. We know that the point 2, minus 1, 0 is on the plane, thus it must make the equation true. So we sub it in. 3 times 2 plus 4 times negative 1 plus 5 times 0 plus d equals 0. We get 6, take away 4 plus d equals 0, and therefore d has to equal negative 2. Okay, again, the question was determine the equation of a plane, so saying D is not the answer, right? We need to actually give the answer. 3x plus 4y plus 5z. We take that plane and put it into the equation. So here 3x plus 4y plus 5z take away 2 equals 0. You can see that yes, it does pass through the point 2, negative 1, 0, which is A there. That point is on the plane. And it has the normal 3, 4, 5, which is perpendicular to the plane. So that's no problem. If you're given a normal, you're given the normal and the point, that's dead simple. You write down what you know. It has to be ax plus by plus cz plus d equals 0. Sub in the point and you'll be able to work that out. Now, find the scalar equation of this plane. Now here's a more interesting question. To get the scalar equation of a plane when we know the vector equation, we need to think the scalar equation, what we just did above, we know we can work out the scalar equation if we have a point plus the normal. Now we definitely have a point here. The point is 2, negative 5, 1. The problem is we don't have a normal, or at least it doesn't seem that we have a normal. Recall though that a normal is perpendicular to every vector on the plane. So think about that for a second. If these two vectors here, 2, negative 3, 0, and 1, 1, negative 1, are vectors on the plane, and they have to be because they're the vectors that are defining this plane, then what we could say here is that the normal, right, would be equal to the direction vector, the direction vector of, let's call it M1 so that we don't mix this up. M1, okay, crossed with M2. And what that will do, remember, what does the cross product do? It takes these two vectors and creates a third vector that's perpendicular to both of them, and that's what we want. That's what our normal is. It's perpendicular to both direction vectors. So we can quickly fire this off. Remember our pattern, we're doing this as y, z, x, y, and we'll just fill in the coordinates. Negative 3, 0, 2, negative 3, and then 1, negative 1, 1, and 1. And we'll do our x patterns here. So for the first one, we do negative 3, negative 1, take away 0, and 1. And that, of course, gives me positive 3. Then the middle one, I'm doing 0 times 1, take away 2 times negative 1. That's giving me positive 2. And in the final one, I'm doing 2 times 1, take away negative 3 times 1, which gives me 5. So this means that the vector here, the normal to the plane, is 3, 4, 5. Okay, sorry, 3, 2, 5. Right, this vector is normal to the plane. Now I have a point, I have a normal, and I've just turned this question into the same question we had above. We know the normal, we know the point. All we have to do now is go 3x plus 2y plus 5z plus d equals 0. We fill in the point that we know. The point is 2, negative 5, and 1. Equals 0. And then we come to this conclusion that 6 take away 10 plus 5 equals, plus d, equals 0. 6 take away 10 is negative 4 plus 5 is 1. So therefore d has to equal negative 1. And we arrive at the answer 3x plus 2y plus 5z take away 1 equals 0. This plane is the equation of the plane that we started with. They are the same. They will produce the same picture. Okay, let's take a second to prove that. So let's draw the original plane. Remember, GeoGebra is fine to draw a plane with a point and a vector. So 2, negative 5, 1. So A equals 2, negative 5, and 1. So there's the point it has to pass through. The first direction vector is 2, 2, negative 3, 0. The next vector is 1, 1, negative 1. Okay, so notice I've got a point, I've got direction vector 1, M1, direction vector 2, M2, and then I can say plane, point, M1, M2, right? And what this is going to do, it creates a plane, right, that's parallel to the two vectors I asked, and passes through the point I want. Now again, it kind of looks like this doesn't pass through the point, but if I simply zoom out a little bit further, you'll see A is definitely on that plane. Okay, again, if I look carefully at the plane, the equation that GeoGebra created, 3x plus 2y plus 5z take away 1 equals 0, which is exactly what we said, right? 3x plus 2y plus 5z take away 1. Now note, GeoGebra sends the d to the other side, but of course it doesn't matter. You put the d, we're going to put the d on the left side. GeoGebra puts the d on the right side and changes its sign. Okay, really, really important skill. How do you translate from scalar equation to vector equation? Okay, so this is, from vector to scalar, which is what we just did. Cross the direction vectors. That will tell you the normal. Once you know the normal, you already know a point, and then it's simply a question of using the formula to plug in the point, and that will tell you the d value. Okay, find the scalar equation of the plane that contains these 3 points. So again, here is a slightly different take on this question. We know that 3 points is enough information to specify a plane, but again, in order to create a scalar equation, what we need, 1 point and 2 vectors, right? Let's put it this way, 1 point and 1 normal. And how do we get 1 normal? We cross 2 vectors which we know are on the plane. So again, let's take a look at this one in 3D for a second and help you visualize before we start. So the first point is point A at 1, 2, 3. The second point is B at 4, negative 2, 4. Okay, and the final point is at C, 5, negative 3, 5. Okay, now those 3 points, we can imagine, if we put all those points in a straight line, right, you can imagine the plane, the surface that all 3 of them would have to touch. You know, we can draw it too. GeoGebra can draw a plane, A, B, C, right? And it just created the scalar equation for us. So we kind of know what our answer is going to be now. But you can imagine those 3 points create a plane. As long as they're not in a straight line, they'll always create a plane. So what we need, though, to create our normal, we said we could really use 2 vectors that we know are on the plane. Well, if you have 3 points, you definitely have 2 vectors. Let's do vector B to C. Okay, there's one of the vectors we need. So 1, minus 1, and 1. So here we go. BC equals 1, minus 1, and 1. Let's create another vector, AB. Okay, so there's AB. Oh, sorry, moved it. Right, there's vector AB, 3, negative 4, and 1. Now I have 2 vectors. Right, I have 2 vectors. I have a point. Therefore, I have the same situation that I had in part 2. I'll cross the vectors. That will give me the same situation I had in part 1. I sub in and give the answer. Okay, so again here, just we can do our cross product. We'll just do it a bit quicker this time. So we have negative 1, 1, 1, negative 1 for the top vector. For the bottom vector, we have negative 4, 1, 3, negative 4. Again, it doesn't matter which one you put on top or bottom, because you know that one normal will point up and one normal will point down, but both will work perfectly fine. So here we find that the normal is equal to negative 1 take away negative 4, which is 3. Then we have 3 take away 1, which is 2. And finally, we have negative 4 take away negative 3, which is negative 1. Therefore, our equation is 3x plus 2y take away z plus d equals 0. We know that it must pass through the point 1, 2, 3. So 2, 2 minus 3 plus d equals 0. And therefore, we can say 3 plus 2 take away 3 plus d equals 0, and d must equal negative 2. Our plane then is 3x plus 2y take away z take away 2 equals 0. And if I go back and look at what GeoGebra did, 3, 2, so I must have made an error here. Oh, sorry, this here, 2 times 2 gives you 4, my mistake, and then you have d is equal to negative 4. There we go. Okay, so that's going to be the equation of that plane. So notice the way this builds up. First we did a point and the normal, then we learned different ways of getting the normal.